All right, we are ready to solve some exponential equations. A little more difficult than maybe the ones that you've seen in the past, but we should be able to handle this. So the I can statement is I can solve exponential equations using the equality property. So let's write equality right here. So using the equality property. Now, there are lots of different types of exponential equations. Most of the ones we're going to solve today are pretty basic. They're a little more complicated than the ones you may have seen in the last year or two. But they're kind of a good stepping stones to some of the more difficult ones you'll see in high school. So let's go ahead and take a look at the warm-up and remind ourselves of a couple of things. First of all, a few of these are squaring. Make sure you pay attention to what the exponent is. We're really familiar. Hopefully you've got quite a few perfect squares and perfect cubes memorized. But remember, exponents are just a way of showing repeated multiplication. How many times we use that base as a factor in a multiplication problem. So 1 squared would mean 1 times 1, so that's going to be a 1. 5 squared would be 5 times 5, that's going to be 25. And again, the quicker you can rattle these off, the better. All of those so far are in your multiplication table, so you should be in good shape. Same with this one, 64. Now, cubes, those are a little more difficult because they get really big really quickly. So 4 times 4 is 16, times another 4. This is going to be a 64. 64 is one of those unique numbers that appears on both the list of perfect squares and list of perfect cubes. Let's see, 3 cubed, hopefully you've got that one down, that's 27. 5 cubed, that's one of the bigger ones that we usually like students to have memorized. That's going to be 125. Notice that I'm giving you a little bit of time to think about these before I write them. And then we've got 2 to the 5th. So now we've got the exponent of 5. So that means we're going to do 2 times 2 times 2 times 2 times 2. So 5 2's multiplied together. So 2 to the 3rd is 8. Times another 2 would be 16, times another 2 would be 32. So 2 to the 5th is 32. Again, really helpful to have a few of those, especially powers of 2 memorized. That's going to come in handy. And then 10 to the 5th. I am hoping that that one is not too bad, because if we multiply 10 5s together, we're definitely going to have a 1 in there. And then remember, we just put another 0 for each one of those 10s that we put on there. So we have this. We've got 100,000 there. So 10 to the 5th is 100,000. It's a 1 followed by 5 zeros. So pretty cool rules for powers of 10. And then the product rule and the quotient rule and power rule and negative exponents, we've talked about those before. Hopefully you learned those really well. Remember, when you're multiplying exponential expressions, if they have the same base, then you add the exponents. So this would be x to the 7th. When you're dividing them, you do a subtraction problem. I generally like to subtract the smallest one from the other one. So on this one, I'm going to subtract the 2 on the top from the 5 on the bottom. Best way to write this is going to be x to the 3rd. There are some other ways to write that. We're going to deal with that in just a second. We'll come back to that. So there were 2 on the top, 5 on the bottom. These 2 are going to cancel with 2 of those, leaving 3 of those x's on the bottom, and of course just a 1 on the top. If we've got a power raised to a power, we multiply those exponents. So this is going to be x. Whoops, let me make that look good. So this is going to be x to the 10th. And then, of course, with negative exponents, the negative in an exponent means reciprocal. So what we're going to do is we're going to take this and we're going to move it from the top and we're going to put it on the bottom. So by moving it from top to bottom, it just changes the sign of the exponent. It's still x to the 5th. We just don't have a negative on it anymore. So this would be 1 over 7 squared, which if we simplified would be 1/49th. Now let's go back to this one right here, and I just want to reiterate. You may have been told you always have to subtract the bottom exponent from the top exponent, which would be totally okay. So I'm going to kind of skip over this one here. So this is going to be x to the 2 minus 5. So that would be x to the negative 3. And then, of course, negative in the exponent means reciprocal. So this is going to be 1 over x to the 3rd. So you'll notice that this one is the same as that one. So we end up here. I like this just a little bit better. It seems to make a little bit more sense. It also leaves us with a positive exponent, and we generally don't like writing things with negative exponents. Okay, let's turn our attention to the actual problems that we're going to be doing here. We're going to use our equation solving skills on some things that look really awful, but they're really not that bad. In fact, I really think you're going to like these, because all we need to do is remember what the equality property of exponentials is. So as long as the bases are equal, and that's really the key here, and all of them are going to be equal on the ones that we do here, then the exponents must also be equal. So if we take a look at this right here, we've got 8 to the m equals 64 to the m. Now, you may remember from seeing these in previous years, you might have to rewrite both of these using a different base. So the good news today is all the problems that we're going to do, if you're wondering, gosh, I could use a 2 for both of these, I think I could use a 4. You might want to think about whether or not you can use a 4 as a base for an 8. You can, but it would be really weird looking. Can I use a 2? Can I use a 4? Can I use an 8? What do I use? At least one side will always be written with the correct base. And it's usually going to be the smaller one. So this is 8 to the m. And remember, we had 64 up above here. That's why it was on there, just as a reminder. 8 squared is 64. So 8 to the m equals 8 to the second. If the bases are the same, then the exponents are the same. So on this one, that means m is going to equal 2, and we are finished. Literally, we are done with that problem. There's nothing else to do. Now, they're not all that easy, so I want you to notice that on this one we've got this ugly looking exponent on the 3. So this is 3 to the 4p minus 1, and then on the other side we've got 3 to the 5th to the 7th. Well, this is a power raised to a power, so again we multiply those, so this is going to be 3 to the 35th. My gosh, that is a really ugly exponent over here, and this is probably one of the bigger exponents I've seen. So here's what we want to worry about. This is the nice thing. If the bases are the same, we can kind of completely ignore those. It's almost like we just get to cross those off, and we just get to say this: 4p minus 1 is equal to 35. And then we've got a regular old equation. We kind of our heart rate should be back down near normal now. So let's add 1 to each one of these. So this is 4p equals 36. We're going to divide both sides by 4, and we get p equals 9. So after that big ugly mess that we had up here, we just get p equals 9, and we're done. Now, what does that solution mean? It means if we plugged this in here, we would get exactly the same number that we would have over here. Now, exponentials get really big. Checking this on a calculator would be a bit of a pain, so we're just going to leave it at that, and then we're going to take a look at the next one here. So on this one, just like our normal rules, this is the exponential term right here. Okay, this is the variable term, if you want to call it that. So we want to move the 100 to the other side. We want to move those constants to the other side. So we're going to add 100 to that side right there. So we're going to get 10 to the 3x minus 4 equals, and that would make 10,000 right here, if I'm not mistaken. So yeah, so another 0. And then we've got to write both sides using the same base. Well, remember, at least one side's going to have the correct base on this. It's certainly not going to be 10,000. So let's write this: 10 to the 3x minus 4 is equal to, remember that we talked about up above? The number of zeros tells you how many 10s were multiplied together. So this is 10 to the 4th. So if the bases are the same, that means the exponents are the same. Again, we're just using that property of equality for exponentials. So the 3x minus 4 is equal to 4. I'm going to add 4 to both sides, cancel that off here. We end up with an 8, divide by 3, and we get x equals 8/3. Now, we don't have to worry about taking this and plugging it back in. It would certainly work. You'll notice that if we did plug it in, we'd have 3 times 8/3. The 3's would cancel. A bunch of cool stuff would happen. The point is, we've solved each one of these correctly. We've written them both sides with the same base. We've set the exponents equal to each other, and then we've used some legal algebraic moves in order to solve that. So we're in really good shape there. Okay, let's turn our attention to this. This one looks kind of weird, but let's go ahead and deal with this. This is 5 to the negative n minus 3, and then we've got 625. Now, if you need to, you can always grab a calculator. So the quickest one for me to pull up is my old TI-83. It's a little smaller, but we can deal with that. It'll look a little bit funky. So here's what I'm going to do. I know that's got to be a power of 5. Now, if you know which one it is, that's great. So I'm going to raise that to the second power, even though I know 25 is not big enough. Then I'm going to do 5 to the third. We talked about that one earlier. So let's try 5 to the 4th. And lo and behold, there it is. So I've identified the correct number. So this is 5 to the 4th. The bases are the same, so that means negative n minus 3 has to be the same as 4. And then we'll just go ahead and solve this. So we're going to get rid of that. So we have a negative n equals 7. So that means n is equal to negative 7. Circle that. We're done. Okay, this one's kind of interesting. We've got a 49 in the denominator. We're probably not going to use 1/49th as a base. Probably not going to use 49 as a base. We probably ought to use 7 as a base. And here's where we've got to put our thinking cap on and use all the different skills that we know about exponents. So I'm going to write 7 to the 2x on this side, and then I'm going to do this. Now, 49 should look familiar. That's 7 squared. So I'm going to write 7 squared here. And then we can use that property of exponents that says if you move an exponent from top to bottom or bottom to top, it changes the sign of the exponent. Remember, the negative means reciprocal in the exponent. So this is 7 to the 2x equals 7 to the negative 2. Now let's just take a look at this and make sure we're good here. 1 over 49, that would be the same as 1 over 7 squared. And 1 over 7 squared would be 7 to the negative 2. By moving this up in the numerator, it changes the sign of the exponent. If you started right here, you'd know, oh, I just need to move that into the bottom, and then it would be 7 squared in the denominator. So I think we're in good shape here. Bases are the same. Oh my gosh, look how easy this is. We're going to divide by 2, and we end up with x is equal to negative 1. That's it. All finished. Okay? Now, on this last one, you'll notice that we've got a 1 over 64, so we're going to deal with it in a similar fashion that we did right here, and we've got a base of 4. So you might look at that and say, gosh, I could use a base of 8 for this. I could also use a base of 4 or a base of 2. But each one of the problems is going to have at least one side that's written with the correct base. Now, it is true we could use 2 as a base for both sides, and we could solve it that way. We're going to keep it simple. We're going to leave this one the way it is. You might want to think about whether or not you can use 8 to write a base 8 to write a 4. That's a little bit sticky, so we're gonna keep this a little bit easy. We're gonna leave this a 4, so we're gonna write 4 to the 5x minus 7. And then on this side, we talked about this up above. It was in the warm-up. That is 4 to the 3rd. So just like we did here, we're gonna go from bottom to top. That's gonna change the sign of the exponent. So we've got 5x minus 7 here. Once we've got the bases the same, then the exponents have to be the same. So negative 3 is equal to 5x minus 7. We're going to add 7. That's a 4 equals 5x. We're going to divide by 5, and we get x equals 4/5. So we're all set to go. Now, if we wanted to, we could double check this, and I am going to go ahead and double check this on this one right here. So I'm going to change colors. You don't have to do this. I'm going to take this, and I'm going to put it right there. Now, this should equal 1/64. So let's just check. This would be 4 to the 5 times 4/5 minus 7. So the 5s are going to cancel. So this is 4 to the 4 minus 7. Which would be 4 to the 4 minus 7 is negative 3. That would be 1 over 4 to the 3rd, and that is 1/64. Okay, so it does equal the other side. So we've solved this. That number right there, when we plug it in, it makes the equation true. All right, good luck on the assignment.